Hi, the aim of this presentation is to give you an overview of my optional module called Nonlinear Optics and Imaging. So the aim of this module is to really look at what it means to take an image and how we create an image. So in the example that I've shown on the right-hand side, we're looking at this beautiful picture of a camera take an image of some mountains. And what we're seeing here is an image created by the interaction of the light coming from the sun, the radiation, the electromagnetic energy. And we see all the different colors and features within the image, and they appear the way they do because of how the light interacts with them. So the grass at the bottom appears green because of the chemical composition of the plants and the trees, and the chlorophyll absorbs everything but the green light, and that's why they're green. The sky appears to be orange because of scattering, and the blue light is scattered out sideways, and only the orange and red light travels forwards to us. So we've evolved to interpret this image and to naturally just understand and be able to interpret how light interacts with materials. But obviously, as physicists, we know that the electromagnetic spectrum extends beyond the visible range, and we can take images at different regions of the electromagnetic spectrum. So we can use thermal imaging, we can image in the infrared to look at heat maps. For example, we can see the heat map from this city. We can use image intensifiers to image infrared light emitted so we can see in the dark. And then in the bottom picture behind me, we can use microscopes, and we can choose very different wavelengths of light. We can pick UV excitation, so we can see different electronic transitions in materials to understand the chemical composition. So in terms of creating an image, it's all about contrast and harnessing the light matter interaction so that we can reveal hidden information about the sample and understand what it's made of and how it works. So light matter interaction is fundamental to creating images and understanding what we can learn from material. So one of the things that you'll learn in your core module in your first term next year, Electromagnetism 1, is this thing called induced polarization. So when an electric field is incident upon a material, the material becomes polarized, and the electric field essentially applies a force to charges in materials. The electrons, the things that move because they have less mass, and we get this induced polarization in the material, this vector termed as P, and the electrons get dragged away, and the extent to which they get dragged away is hidden in this term called chi, the Greek letter chi, which is multiplied by the E, and that tells us how easy it is to drag electrons away from material. When we're thinking about imaging with light, we're not just using a fixed electric field, we're using an oscillating electric field. So the electromagnetic radiation from our light source is a sinusoidal frequency, and effectively we're shaking the electrons backwards and forwards at the optical frequency that we're using to excite the sample. And this polarization that we have becomes a time-varying polarization. So if we then look at the induced polarization we get, we're shaking our electrons backwards and forwards around their equilibrium position, and each electron which is being shaken acts as a dipole emitter itself. So the polarization that we induce acts as a dipole emission, and we re-radiate electricity at the frequency that we're driving it at. So if we think about learning about a material based on the response of the electrons to the frequency at which we drive them at, we need to understand how the electrons are bound to the material. So in different materials, electrons are bound in different ways. And what we're interested in understanding is the restoring force experienced by these electrons. So from your recent module, Waves and Optics, you've looked at harmonic motion. And we know that the restoring force in harmonic motion we can describe as linear with the displacement from the equilibrium position. So as we drag the electrons away from their equilibrium position, the restoring force scales linearly with that displacement if we consider them to be a harmonic oscillator. And in that case, our potential well that these electrons sit in takes the parabolic form. So we integrate the restoring force over distance, and we get a parabola term, half kx squared, and we get this nice parabola. So effectively, we're driving the electrons backwards and forth, and they're sat in this nice parabolic potential, and we get this thing, the equation for the harmonic motion of a damped harmonic oscillator, where the electric field is the driving force. But where it becomes interesting is in real materials, the potential that the charges sit in isn't always considered to be a parabola. So at small displacements from the equilibrium position, we do indeed see a linear restoring force, and we experience a parabolic potential. But as soon as we start to drag the charges further away from their equilibrium position, this starts to become non-parabolic. So the further we drag them away, or the higher the electric field, the response of the material is no longer linear with displacement. So if we take our parabolic potential and we drive the charges with a sinusoidal waveform, what we expect to get out, the polarization that's induced, is going to have a single frequency sinusoidal response, a linear response of the sample. The emission from these dipoles is at the same frequency that we use to excite them. However, if we drive the system a bit harder and pull the electrons further away from their parabolic potential, we can start to see that the restoring force becomes non-linear with the position. And in this case, whether we consider the symmetric or asymmetric potential, what we see, the waveform of the induced polarization is no longer a single frequency. And what we get are some very non-linear polarizations with respect to time, and we can now generate optical frequencies from the induced polarization at frequencies other than the excitation wavelength. And this is really the key to nonlinear optics, because it allows us to decouple the excitation wavelength from the energy of the photons that we need to excite the contrast in the material that we want to image. So one of the really important benefits of nonlinear excitation is the trade-off between scattering and the diffraction limit. So if we want to image inside samples, such as biological tissues, one of the real challenges that we need to overcome is scattering. So if you shine a laser beam into some biological tissues, the thing that really kills your signal and your depth penetration is scattering. So scattering is far more of a problem than absorption in tissues, and we find that after a few tens of microns into the sample, visible light becomes scattered and we can't see any deeper. And this effect is Rayleigh scattering, which is proportional to 1 over wavelength to the 4. So this is the reason that the sky is blue and the sunset is red. The blue light scattered out sideways, whereas the red light travels in a straight line. That's why we have a red sunset. And then on the opposite side, one of the other things that we want to achieve when we're imaging is we want to be able to look at small things. And you know from the diffraction limit, when you've looked at the Rayleigh criterion in waves and optics, your diffraction limit reduces with the wavelength. So if you want to look at small things, you want a shorter wavelength. So these two things are at odds. And this is one of the advantages of using nonlinear excitation, because it allows you to decouple the relationship between scattering and the diffraction limit. So in this module, we're going to look at the fundamental principles underpinning nonlinear light interaction and how we can apply these to image into lots of exciting research applications. And I'm just going to give you a flavor of one of them. So one of the things that we've been doing in our labs in physics is looking at microplastics. So clearly we know a lot about microplastics. Nowadays, we know that they're bad for the environment and they accumulate in the marine environment. So maybe about 5 years ago, I was contacted by a lady from biosciences, Professor Tamara Galloway, and she was interested to know about the potential accumulation of microplastics in marine organisms. And this was a really challenging imaging application, because we needed to look at small things, these microplastics, deep inside marine organisms. So we were given some samples of plankton, these little tiny marine organisms that have swallowed microplastics. And we also looked at the gills in fish that have been taken out of the ocean. And using the nonlinear imaging, we were able to see deep inside the fish gills and the plankton and detect the microplastics that had accumulated inside these organisms. And we were able to create these beautiful images that show the accumulation of these microplastics. and the images were used as evidence. So images from our labs in Exeter were used as evidence to go to the government, which resulted, along with other information, into the UK ban on microplastics in cosmetic products, which then went on to be applied across Europe and North America. So this is just one example of something really exciting that has an impact on society that we've achieved using nonlinear optics. So in terms of the lecture course, what will you learn from it? So it primarily builds upon the knowledge that you've gained in waves and optics when we're looking at harmonic motion, damped harmonic driven harmonic motion. And we're also going to build upon some of the core electromagnetism that you're going to learn in your first term next year when you do PHY 2021. So you'll learn about how materials become polarized, how charges respond to electric fields. And then we're going to build upon that and then look at how materials respond in the nonlinear regime. We're going to look at ultrafast laser pulses. These are critical to exciting nonlinear optical processes. We're going to look at how we can make very short light pulses with high intensities and what happens to these pulses when we send them through biological tissues. And we're also going to look at some of the state-of-the-art research applications in nonlinear optical imaging where it can be used. I've given you one example of environmental detecting, but there's loads of other really exciting applications where nonlinear optics can really make a difference. So in terms of why you want to do this module, it will expose you to some cutting-edge state-of-the-art imaging. It will hopefully challenge or make you think about what happens when light interacts with material and how we can harness that to learn about the material. There's not too much maths in the module. The nonlinear light matter interaction builds upon the maths that you would have learnt in electromagnetism 1. And a really exciting part of the lecture course is that you get to have laboratory demos. So we get to visit the nonlinear optics labs on the second floor in physics, and you get to see what's going on inside our active research laboratories. So if you have any more questions or would like to ask me about the module, please drop me an email. Bye.